CHS DFO applications, for us, the primary use is coastal and shallow water mapping, in particular remote areas. We're anxiously hoping to do Arctic charting with LiDAR. And obviously areas of, you need good water column properties, good water visibility, clear water, calm water preferably, although not perfectly calm because then you get too much reflection on the surface. Again, with LiDAR, you can deploy a LiDAR project quickly because it's aircraft, whereas with boats in remote areas, it takes a while to get there in ships and possibly ice problems in the Arctic. All of our work is very seasonal, of course, here in Atlantic Canada. Repetitive surveys is a logical one. I mean, if you're in Shediac today, you'd see why, because the wharf keeps getting, the shoreline keeps getting washed away there. So repetitive mapping for coastal hazards or coastal erosion, sea level rise in our case. Within DFO we have something called operational oceanography, or a coastal hazards project that's not terribly active, but the LiDAR technology would be very suitable for monitoring changes in coastline, obviously, and the seabed also for us. Loft to sea baselines. The basis for all of our offshore boundaries is our baselines, and they're defined as either the low water line on the larger scale national chart, or in the case of where there's open bays and harbors, you pick a series of points at the furthest extent of your shore, which means detecting and measuring any offlying drying rocks is very important to delimiting offshore boundaries. So one of the ways to map those is, of course, with LiDAR or other airborne systems. Shoal or wreck detection, we again, usually because of limited resources, sometimes we are reduced to just serving a safe route for navigation. So one option that has been tossed around is maybe we could fly LiDAR over a selected route, and if you get any returns less than 30 meters, it's probably a hazard to shipping. If you get no returns, then is it reasonable to assume that the water is deeper than say 30 meters, or whatever the expected maximum return in that area might be. It's I don't think we've done it to date, but it's an option that people seem to think might be worthwhile. But if you don't get any data return, then I don't think that's reasonable. It'd be difficult to assume what the minimum depth would be. Habitat mapping. We work with other parts of DFO and other departments, of course. And so LiDAR also gives reflectance, which is the amplitude or shape of the return pulse, and from that you can infer the type of bottom along with other ground truthing information. So there's a data set that's standard output from LiDAR systems of reflectance, which is analogous to a mosaic, a grayscale mosaic, generally is what they deliver these days, which can be used for seabed classifications, fish geology, possibly eelgrass detection. I know some people at BIO we work with that are keen on finding eelgrass. But there's plenty of research needed here to work on the pulse return as more people get involved. So as I mentioned, CHS, our priority is for LiDAR. Our main application for LiDAR is the littoral zone from above the high water line, just into the topographic area, through the foreshore, and past the low water line, out to whatever depth we can get with the LiDAR system, and then to join up with existing data usually from acoustic multi-beam systems these days. This is a very difficult area to work with boats and other systems. Sea conditions, shallow water, usually shoal infested, treacherous. So a few samples of some of the projects. Unfortunately, I don't have a nice overview of all the sites, but we did about 12 sites. I'll just mention this project first. A national project of several groups and departments, CHS, DFO, Parks Canada. It was a Parks Canada-led project to go for the TER and the IBIS, the Franklin expedition lost boats. It's basically an archaeological type survey. Anyway, we teamed up with us, University of Victoria, Canadian Space Agency for RadarSat and other satellite imagery, Environment Canada, and National Defence. Just the overview. So it's in the Arctic. This is Victoria Strait, so-called, well, one of the Northwest Passages, and this is Baffin Island there to the east. So the Franklin ships supposedly disappeared here just west of King William Island, I forget what year, 18-something, and ever since people have been fascinated trying to find them. So we were part of this project. We flew a LiDAR. This was an area of interest. It was very shallow, and we flew the LiDAR. I don't have an update on the project. It was just done late August there. So there was multiple sensors also involved. We had acoustic systems, side scan, multi-beam. Parks Canada had high-res side scans, I know, looking for the wrecks. But I think the project was successful. I haven't seen the data, like I said. This is just the Frugro. Well, it's an aircraft. It was a King Air 90 that houses the LiDAR system. It's a charter aircraft. Mostly, there's 2 boxes of electronics here, and the laser, there's a hole in the fuselage here where the laser is fired. Some of the issues, weather issues are a big issue. Like I said, first of all, you have to be able to fly, and preferably good water conditions. So our project was it was year-end funding as usual. So we were trying to swing this last week of March and early April, and it's hard to find good weather in Atlantic Canada, but we got some good results. Ice coverage was an issue. We couldn't go too far north because the Gulf was full of ice, northern Newfoundland was full of ice. A lot of Nova Scotia and the Maritimes area, turbidity, Bay of Fundy are prime areas, but turbidity is a big issues there. North Humboldt Strait, turbidity is a big problem. So rather than take a risk, we tried to pick sites that we thought would give good results, because it was sort of penned as a demonstration project to show that we get charting quality data, and so our managers can go find big funding chart the Arctic. We also had some collaboration with private sector partners. You might know Nalcor and Emera are planning a maritime link, a power cable from Churchill Falls, Labrador, down through Newfoundland and across the Cabot Strait. So this is Cape Ray, Newfoundland, Port aux Basques area. This area has also never been charted since deadline in 1850s, and also in finding some landing sites for their cable. So we were doing the LiDAR anyhow. So they co-funded some of the work there, in particular processing. So that's a sample of what we got reasonably good results in Cape Ray. This is Wreck House, the highest winds in the world are there. We got about, I think about 20 meters. So what did we do with that data set? We're processing it for charting, but in conjunction with GSC, our geologist at BIO, John Shaw, we've taken, so I'll just go through these four. So this is the LiDAR coverage. So then we went back with our acoustic multi-beam systems and started where the LiDAR left off, which is about here. And then we surveyed this with the Matthew and multi-beam systems. So you can see the nice combination merger of multi-beam acoustic LiDAR and topo DEMs to have a good seamless data set. It's very critical to ensure a good comparison of the data sets, to use similar or the same positioning systems, and in particular vertical control. For our surveys, we everything was referenced to the ellipsoid, so the horizontal positions were, of course, but in particular the vertical was, so we got height above the ellipsoid for all the LiDAR points. And then we have a tide datum, a chart datum ellipsoid separation model. So the depths on our charts got to be referenced to chart datum, which is low water, so which varies a lot. So we have a model then to transform the values from ellipsoid heights to chart datum. So then the GSC took out some of the ground truthing data and looked at the backscatter from the multi-beam and did a superficial geology interpretation in these two slides, which is very useful for coastal hazards analysis in the GSC, and will be helpful to Nalcor in picking a landing site. The next step would be going to habitat mapping type analysis in those areas. So this is an example of the project from the eastern shore of Nova Scotia. Ecum Secum we called it. Again, it's a very rugged, it hasn't been never charted since the 1850s. We've been down there with boats for many years, and we keep running aground and beating them up. So we flew LiDAR and we got good results out to about 25 meters, 24 meters, probably mostly 20. So our plan is to make a new electronic chart out of that area, of that chart. And so now we're going back. We've done what's outlined here in gray, and these boxes are gaps. We took the LiDAR data, looked at all of our historical existing data, identified gaps or holes, and now we'll go back to the multi-beam acoustic systems and fill in the holes. And we, at the same time, we'll ground truth the LiDAR.